Okay, we're going to take a look at how to write electron configurations in this podcast. It can be a little confusing, so it will help you to pay attention to this podcast.
What we're really trying to do is map out where all the electrons are using the periodic table and figure out how the periodic table is set up. Electrons, we know that they're around the nucleus, but it's a little more complicated than that. They exist in different energy levels.
I think most likely what you've been taught up until now is that electrons are in orbitals, and the image that you probably have in your head is that they are similar to planets orbiting the nucleus, and that is not really true. It's more complicated than that. So we have energy levels for the electrons, numbered 1 through 7, based on how far they are away from the nucleus.
So the farther they are away, we give them a higher number.
Yep.
And that kind of fits with what you know about them. Some are closer, some are farther away. But then there are sublevels. Now this is totally new. You've got 4 different types of sublevels: S's, P's, D's, and F's.
And it says each one holds a different amount of electrons. So the S's are the smallest, the S sublevel is the smallest, then the P, then the D, and the F being the biggest.
And those also have to do with shapes, which we might get to later. And then within the sublevels, you have orbitals, and that's where the individual electrons are actually found.
So get the picture out of your head that these are orbits like planets. That's not what they are at all. They're technically probability regions, so if you're really into statistics, you could...
It's just a location.
Yeah.
And the orbitals, each orbital holds 2 electrons. Electrons always come in pairs. That's going to be important.
Yeah.
So let's take a look at that really quick. Let's look at the 4 different types. We've got the sublevels, the S sublevel, that holds 2 electrons.
And has 1 orbital.
Because those electrons are paired up.
Yes.
The P's hold 6.
Has 3 orbitals.
Pair them up, you get 3 orbitals.
Yeah.
The D's hold a little bit more. There's 10.
So they have 5 orbitals in the D.
And the F's, 14.
7 orbitals.
Pair those up, you get 7 orbitals.
Yeah.
Now, you might be asking, where do those come from? Why does it look like that? And it's actually quite simple. If you get out your periodic table, you're going to see why it's arranged the way it is with those 4 orbitals. You've got the S, P's, D's, and F's. You might notice your periodic table has different regions. If you kind of block them out like this, there's 4 different sections. What do you think those correspond to?
Well, there's 4 different orbitals.
Sublevels.
Sublevels, you're right.
There are 4 different
sublevels. 4 different sublevels.
S's, P's, D's, and F's. Let's start with the S's. You can see there that helium is technically part of the S. It kind of fits into that first block. That's the S orbital. And then you've got the P's, D's, and F's. So if you remember, the S's have 2 electrons. It's because there are 2 elements in each one of those rows in the S. P's have 6. There are 6 elements in each row in that group. The D's have 10. There's 10 elements in each row. The F's have 14
so
because
14
there's 14
elements
in that row,
yeah.
In each row. So that's kind of how they're broken up. So where do the energy levels fit in?
The energy levels are represented by the rows or the periods of the periodic table. So there just so happens to be 7 periods in the periodic table. And it just so happens that we only have 7 energy levels that we know of right now.
So the farther down they are, the bigger the atom, then its electrons get farther and farther away. Now you look at the S and the P's. If you want to know the energy level for the S and the P, look at the number of the row that it's in. That's not true for D and F's.
Yeah, D and F's are a little bit more complicated. The D sublevel, to figure out what energy level that is, then you take the row number and subtract 1 from it.
So if you find copper on your periodic table, copper is in the 4th row, right?
Yeah.
What's the sublevel, or what's the energy level?
So the energy level for its D sublevel is the 3rd energy level.
So copper is technically in the 3D section.
Yeah.
Because it's in the 4th row, but you subtract 1. So that's energy level 3, and it's in the D. So we say copper is in the 3D section. Okay? And you can see that here.
The F's...
Oh, I'm skipping ahead here. F's.
Actually, the row number -2 for the F's. And if you don't remember, the F row, the F block, is what we sometimes call it, fits right in between the S's and the D's. So
and it's in rows 6 and 7.
Yeah.
Subtract 2. So there's a 4F and a 5F. we have to remember that the electrons, they come in pairs. So we already kind of talked about this. For the S's, there's 2 elements in each row.
Which means they can fit 2 electrons.
So there's 1 orbital.
1 orbital for the S.
There's 6 elements, 3 orbitals in the P's, 5 orbitals in the D's, and there's 14 elements, so 7 orbitals in the F's. We're going to use that a little bit later in the podcast, but just remember that electrons come in pairs.
Yeah, right now this may seem a little bit confusing, but when you actually start applying what we're talking about right here, it becomes a little bit more clear.
We're just giving some definitions right now. So here you go. Here's the periodic table with all the lines in it. You can see the S's and the P's correspond to the row. You've got the 1s row, the 2s row, 3s, 4s, etc., 2p, 3p, 4p, and that makes sense.
In the D's, you can see that there's a 3D, a 4D, a 5D, and a 6D, and then you
subtract 1.
Right, and then you jump down to the F's. You have to subtract 2 from each row number, so there's a 4F and a 5F.
Yeah. And this is where you get to writing electron configurations, and it's just like reading a book. If you can read a book, you can write an electron configuration. First thing we want to do is we want to figure out what element we're going to talk about. Let's do copper. It's in 3D. We already talked about it a little bit. We're going to map out where all of its electrons are. Okay? So, where do we start?
We're gonna start at the top left of the periodic table and go from left to right, and then
top to bottom,
left
to right.
That's right.
Just like you're reading a book. And electrons they fill up the orbitals that are closest to the nucleus, and that's the 1 energy level, because they're the closest. So we're going to start there. We're going to pull the 1s orbital out, and there's a superscript.
We're basically going through the periodic table until we get to copper. And once we get to copper, we'll stop writing the electron configuration.
And there's 2 electrons from hydrogen and helium in those positions. So we give it a superscript. The 1s orbital has 2 electrons.
Yeah, so in the first energy level, we have an S sublevel, which has 1 orbital, which fits 2 electrons in it.
Second row, 2s, S's have 2 electrons. Then we go over to the P, because you're just going across the entire row. You get to the P next. P's have 6. So we're just filling all of these up until we get to where we want to be at copper.
Okay, down to the 3s.
3s, there's
2. Again.
P's, 3p, 6. Next row, just like you're reading a book. 4s, 2 of them there. And now we get to the 3D. Now, how many do D's have?
D's have 10, but it looks like copper doesn't quite go all the way to the end of the D.
You're right. Copper stops short a little bit. So we want to figure out exactly where copper is, and we're going to stop there.
So we know it's 3D.
And it's in the 9th position. Count them over. You can see copper's 9. Zinc is next to it. Zinc is 10. So when you get to the end, in your last element, stop where your element is. We've got copper ends in the 9th position. It only has 9 electrons in that orbital. That orbital is not full.
So you might be thinking, why can't I just write 3D9 and that be copper? Well, technically, someone who knows what they're doing would understand you're talking about copper, but the proper way to do it is to show all of the electrons.
And it has 29 electrons if you look on the periodic table. 29 protons, 29 electrons. If you add up all those superscripts, you get 29. That's what copper has. Let's try one more. Tungsten, a little further down. All right, we're going to go through these a little bit quicker. Just like you're reading a book, 1s, 2s,
2s2,
2p,
2p6,
third row,
3s2, 3p6,
4s2. You just fill each one as you come to it like you're reading a book.
3d10, the D's get in there in between the S and the P there.
5s, it's getting longer.
5s2, 4d10.
Yes, they are this tedious.
5p6.
6s. All right.
Here's a little tricky
6s2.
spot.
Now we go to 5d, right? No! Remember, the F block is technically between
the S and the
S's
D
and the
right
D's.
there, down in row 6 and 7.
So after 6s, we really get to 4f.
And how many were there in there? 14. So it's 4f14.
Don't forget about the F block for the bigger elements. Then, if you just follow the atomic numbers on your periodic table that go in a logical order, after you're done with the 4f, it goes back up to 5d. And tungsten did not fill the 5d sublevel. It's in the 4th position. So 5d4. That's how you write an electron configuration. Wow, that's tedious, but it maps out where each electron is in each element. Oh, there's a short form.
Oh.
Thank goodness.
Yeah. So this is really just a shorter way to write the electron configurations that we just wrote. It's a shorthand, essentially.
So let's pretend that we did all this by hand. For bismuth, find bismuth all the way at the bottom in 6p, and it's the third one, 6p3. So it fills up every orbital before that, including the f's, and it gets back to 5d10 and 6p3. Now, that's really long. I don't want to have to write that every time.
Yeah, so what we can do is you go start from the end of the electron configuration and work yourself backwards until you see a P6.
Okay, because what does P6 represent?
The P6s are all of the noble gases.
The noble gas
So
configuration.
we want to go to the farthest one out.
So we're going to find the noble gas. Another way to look at it, if you look at your periodic table, find bismuth, find the noble gas directly before it, in the row above it. Okay?
Just so happens that it is
Xenon? Xenon.
Yeah, it's xenon.
Okay, it is xenon.
Had to
So
double check.
Xenon, here's what we do. Since noble gases have a full orbital, or a full energy level, we take that energy level that ends there. There's xenon, right? Inside the brackets,
That's right.
5p6.
Xenon.
All of those represent xenon. So we take those brackets and we smoosh them together and we write xenon. So,
And then we have some stuff left over after the brackets.
so bismuth is really the same electrons that xenon has
plus some extra.
plus some extra. So start at xenon and then read just the last row of bismuth.
And we really just use the noble gases because they're kind of special elements. So,
And they have full energy levels.
Yeah,
It's
exactly.
full electron energy levels. So
Exactly.
try this one then. Let's look at silver. Find silver. And before we put it up on the screen here, pause. Find the noble gas that comes immediately before it, or the P6. Which one does that represent?
that look,
There's your
so that looks
there's
like
your noble gas.
krypton right there. Comes
That's
before
krypton.
Silver.
So hopefully you found
That's
krypton.
That matches.
Smoosh that together, write krypton, and then start reading from the next row. After krypton, you get to 5s2, and then 4d9, and that's where silver's at. Okay, so once you get the electron configurations, the noble gas for certain elements, especially at the bottom, can be a lot shorter. And then we have orbital diagrams.
Okay, so far we've been kind of we used a shorthand, the noble gas configuration, and we wrote out using the energy levels and sublevels and number of electrons. Now we're actually going to write out and show the energy levels, the sublevel, and the orbitals. So this is the most probably, I guess, complicated. I'm not sure if that's the right word, but
Tedious, maybe.
yeah, it's probably the most tedious.
But it's the most accurate.
Yeah.
It shows where each electron is, especially in the orbitals. It's more specific than just writing superscripts. And we're going to use boxes to represent orbitals. Now, what does that mean? Now we need to know that electrons come in pairs. Because there we have sublevels, but you cannot see the orbitals.
Right. We don't exactly see how the electrons are arranged within the sublevel here. So the orbital diagrams help to show us that. So we're going to take a look at we have the electron configuration of fluorine, and we're going to draw that out as an orbital diagram as well.
We're really just going to translate it. So we've got the 1s are the first electrons that we come across. We're going to draw a box for that orbital.
And the s has one orbital, so the 1s has one box.
One orbital, one box. And that box holds 2 electrons. Remember, the superscripts are electrons. So I'm going to put those electrons in my box. And I'll show you why I'm putting them this way in a moment here. But just kind of, let's follow just the boxes for a moment. The next one, 2s.
This is another s, so only one box.
And I'm going to label it 2s. There's 2 electrons in that box because they come in pairs. So I'm going to put little arrows. You can put full arrows, it doesn't matter. I'll do that on the next one. Or little half arrows, doesn't matter. And now I'm at a P. Now what's different about the P's?
The P actually has 3 orbitals within that sublevel.
And I'm going to
So we
draw
need
all of them.
3 boxes.
3 boxes. It has 5 electrons in it. So I'm going to put 5 arrows. I'm going to draw them that, we'll pretend that's an arrow. We'll draw it like that. And I'm going to label this 2p. Okay?
All right. That's a nice orbital diagram for fluorine.
So 1, 2, 3, 4. There are 5 different orbitals there. Electrons come in pairs, so they get paired up, and then some of them are by themselves because fluorine doesn't have a full sublevel.
Right. Now we know fluorine has, what, 5 orbitals, and one of those orbitals is only half full.
Now you can see where all 9 of those electrons are at, more accurately. Okay? So let's look at some rules. What in the world did we just do? First rule, each orbital gets its own electron before doubling up. So if we had a p orbital,
Right.
there's 3 of them in there.
3. So each orbital, each of the 3 orbitals will have 1 electron before you go back and put a second electron into each orbital. So this really only, this rule only applies to p, d, and f orbitals because the, sublevels, because the s sublevel only has 1 orbital.
It's like the roommate rule.
So they're going to have to double up right away.
There's 3 orbitals in the p's. If there's 3 electrons, they want their own room.
Yeah.
You don't want to share a room, so they're going to have their own orbital before they double up. The second one is 2 electrons in the same orbital. Once they're sharing, they cannot have the same spin. Now that's why we were drawing them one up and one down,
Electrons would prefer to be as far away from each other as possible,
since they're both negative.
but they really want to be close to the nucleus too. So, to solve this issue, they both want to be the same distance from the nucleus if they're in the same orbital. They just face away from each other.
More or less. They share a room, an orbital, but they don't really want to be near each other. So let's look at oxygen. We can kind of demonstrate these 2 rules. All right, we're going to translate this one just like we did the fluorine. Start at the 1s.
And our 1s has 2 electrons in it.
So I'll put 1 arrow up and 1 arrow down.
So this is our lowest energy level, and there's no option for the electrons here except for that they have to double up.
They have to share.
No choice.
2s, 2 electrons.
Again, have to double up.
2p. Now, notice the way I draw these. I'm going to draw them correctly this time, in the right order. Since they do not want to share, there's 4 electrons. I've got 3 boxes, 3 orbitals. Each orbital gets its own electron first.
Okay, now we're going to have to double up.
Then one of them gets doubled up.
Right.
That is the only way to write it. What we don't want to do is you don't want to say that 2 of them are full and then 1 of them is empty. That is wrong.
Yeah, you don't want to have an empty room sitting there. One of those people is going to take up that room instead of having a roommate.
Okay? So there's the orbital diagram for oxygen. And we've got a bonus rule. Draw all the orbitals even if you don't need them or they're not filled. Okay?
So,
a little longer.
Sometimes, like when you have a D or an F, you're only going to have a small number of electrons that fill up that particular sublevel. So you might have some empty orbitals.
It's longer, but let's translate it. We've got the 1s, 2 electrons. Hopefully you're catching the pattern by now. 2s,
2 electrons.
1 up, 1 down. 2p.
That's a full 6 electrons, so each box is going to be partnered up.
Three s.
Another S, just one single box.
Feel free to fast forward till we get to the D. Just in case you feel like this is a long podcast. 3p, single, 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 double, double, double. Where am I? 4s.
Now we're at the 3D.
3D.
This is where we actually have to pay attention.
Remember,
a bit.
the Ds have 10 electrons or 5 orbitals. Okay? No matter what, there are only 3 electrons, but I have to draw all 5 orbitals.
All right.
Okay?
And we have 3 electrons, so each one is going to take up its own orbital within that D, that 3D.
And then 2 of them just remain empty, but they are important. You do have to include them. And just for fun, why don't you pause the podcast as you try and write the electron configuration and orbital diagram for europium. Glad I don't have to do that. Or type it.
That would be awful to have to do that.
Welcome back. Hopefully you got this for the electron configuration for europium. Double check it, make sure it's careful. It goes all the way out into the F's after 6s. And there's your orbital diagram.
Good
as
fun.
well.
Good fun. All right, if you got those both right, congratulations. You win the prize of being done with this podcast.